Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked. How can a blurry image of a star help us understand more about their orbiting exoplanets than a clear, sharp image? It seems counterintuitive, doesn't it? Like trying to understand a detailed painting by stepping back until it's just a wash of color. Yet that's exactly what CHOPS, or the Characterizing Exoplanet Satellite, is doing. Don't worry, we'll take it slow. This isn't a race through equations. It's more like floating through a galaxy of ideas with a cup of chamomile tea, letting the vastness of the cosmos gently unfold around us. Let us drift into this idea softly, like a feather descending onto a calm pond. CHOPS, a pioneering space telescope, was launched by the European Space Agency, or ESA, in December of last year. Imagine it as a finely tuned ear, or perhaps a sensitive eye, sent out into the vast, silent ocean of space. Its singular mission to hunt down the most Earth-like exoplanets. This is no small feat when you consider the truly staggering distances involved. Think of it not just as far, but as an almost unimaginable expanse, where light itself traveling at its incredible speed still takes years, even decades, to reach us from these distant suns. It's akin to trying to spot a single tiny firefly flickering on a boundless horizon from a mountain peak hundreds of miles away. The light from that firefly, so faint and fleeting, must traverse an enormous void before it ever brushes against our detection. CHOPS does not embark on this grand journey alone. It is a joint effort, a quiet collaboration between ESA and the Swiss Space Office. This partnership feels incredibly fitting, almost poetic, because it was Swiss astronomers who, in a momentous breakthrough, discovered the very first exoplanet back in 1995. Pause for a moment with that thought. Can you truly believe that it was only a quarter of a century ago that humanity definitively confirmed the existence of a planet orbiting a star other than our own sun? Before that, they were merely whispers in theory, faint possibilities dancing on the edges of our scientific dreams. It is akin to believing for millennia that our small village was the only one in existence, only to discover just 25 short years ago that the world outside was teeming with countless other bustling settlements, each with its own unique stories and landscapes. When we contemplate CHOPS, we are not simply considering a machine launched into the void. We are contemplating a profound leap in human understanding, a testament to our relentless curiosity. It is a bridge between what we comfortably know within the cozy confines of our own solar system and the grand, mysterious expanse of what we yearn to discover beyond. It serves as a gentle reminder that even as we might feel infinitesimally small within this boundless universe, our spirit of inquiry, our innate drive to explore, is boundless in itself. We are reaching out, not with a desire to conquer, but rather to understand, to connect, to hear the silent echoes from those distant unknown worlds. Each photon of light that CHOPS gathers is like a single word, a hushed sentence in the unfolding story of another world. And our quiet task as listeners is to patiently piece these fragments together, hoping to eventually glimpse the landscapes, the swirling atmospheres, and perhaps, just perhaps, the nascent stirrings of life we have never before encountered. Imagine CHOPS as a silent storyteller, suspended in the cosmic dark, meticulously gathering tales of light from far-off stars. Each flicker, each minute variation in brightness is a subtle inflection in a universal narrative, and these stories are not shouted, they are whispered across the vastness. The challenge, then, is not just to hear, but to truly listen to, discern the faint melodies hidden within the roaring symphony of starlight. This is why CHOPS is so uniquely designed, why its very purpose hinges on seeing the subtle, the almost imperceptible. It is built to notice the delicate brushstrokes that define a planet's existence, not the bold outlines of the star it orbits. This mission, this quiet pursuit of the unseen, truly humbles us. For so long, our understanding of planets was confined to the handful we knew in our cosmic neighborhood. We imagined our solar system as a unique, perhaps even solitary arrangement in the universe. But the discovery of exoplanets, beginning with that first whisper in 1995, has opened our minds to a galaxy teeming with worlds. It's like standing on a small familiar island for your entire life, believing it to be the only landmass, only to then glimpse just beyond the horizon the faint outlines of an endless archipelago stretching further than the eye can see. Each new island, each new exoplanet adds another layer to our understanding of cosmic diversity. It expands our definition of what a world can be. CHOPS, in its elegant simplicity and profound purpose, stands as a symbol of this expanded cosmic consciousness. It is not about grand pronouncements or dramatic visuals. It is about meticulous measurement, about discerning truth from the faint signals that reach us. It represents a deeper, more mature stage in our quest for knowledge. We've moved past merely identifying new dots of light in the sky. Now we are learning to read the subtle signatures within those dots to infer the presence of planets that are too small, too dim, too close to their blazing suns to ever be seen directly. This is the quiet revolution that CHOPS embodies. Consider the human spirit of inquiry. It is an unquenchable flame, always seeking, always questioning. From the earliest stargazers who charted the familiar patterns of constellations, to the brilliant minds who deciphered the laws of celestial motion, to the engineers who now send our instruments beyond the confines of Earth. This journey of understanding is a continuous thread woven through human history. CHOPS is but the latest exquisite stitch in this tapestry of knowledge. It doesn't scream its findings. It gently murmurs them, inviting us to lean closer and listen. The sheer technological marvel of CHOPS is itself a testament to human ingenuity. To design an instrument capable of such precision, able to detect light variations that are almost imperceptible to our terrestrial senses, is truly astonishing. It's like building a musical instrument that can hear the most minute change in a distant echo, a change that signifies the presence of something otherwise entirely hidden. This delicate art of detection, this ability to infer the colossal from the minuscule, is what makes missions like CHOPS so uniquely valuable and so deeply inspiring. It pushes the boundaries of what we thought was possible, reminding us that there is always more to learn, always more to discover, always more to quietly wonder about in the silent symphony of the stars, as CHOPS silently circles our Earth. Riding the boundary between day and night, it collects its daily bounty of light. Each byte of data is a precious commodity, a potential key to unlocking the secrets of a distant world. It's a quiet promise whispered across light years that we are steadily, meticulously drawing closer to understanding our place in this vast, star-strewn universe. The blurry images it sends back are not a sign of imperfection, but a testament to a revolutionary approach, a new way of seeing that might one day reveal the most profound truth of all that we are not alone. And with that gentle thought, perhaps we can begin to truly rest, knowing that out there somewhere the universe continues to reveal its wonders, one soft, blurry image at a time. The universe is a grand library, and CHOPS is one of its most dedicated silent readers, slowly turning the pages, seeking out the stories that matter most to our understanding of existence itself. And in those stories, perhaps we will find not just answers, but even deeper, more beautiful questions to ponder as the stars twinkle softly overhead. Let us now gently turn the page of our cosmic story and drift back in time, not to the beginning of everything, but to a moment that marked a profound beginning for us here on Earth, the genesis of exoplanet discovery. It's truly hard to believe, given that we now have confirmed the existence of thousands of these distant worlds. But it was only a mere 25 years ago in 1995 when Swiss astronomers made that groundbreaking initial find. This humble beginning, seemingly so recent in the grand timeline of the universe, marks us as being in the very early days of this astronomical field. It's as if we've just learned to take our first steps in a vast, unexplored cosmic landscape. Before that pivotal year, the idea of planets orbiting stars other than our sun was largely confined to the realms of science fiction, philosophical musings, or theoretical calculations. Scientists could infer the possibility, of course. Logic dictated that if our sun had planets, it was reasonable to assume other stars might too. Yet, reasonable assumption is a far cry from confirmed existence. For millennia, humanity looked up at the night sky, seeing countless points of light, each a distant sun, and wondered, were we unique? Was our solar system an anomaly, a rare cosmic gem, or merely one among an infinite number of such arrangements? The prevailing view, albeit often unspoken, leaned towards the former in part because we simply had no evidence to suggest otherwise. Our own solar system, with its familiar family of planets, felt like the only neighborhood in the entire cosmic city. Then came that whisper from Switzerland, a quiet but revolutionary announcement that would forever alter our cosmic perspective. It wasn't a sudden dramatic explosion of light or a clear image of a new world. Instead, it was a meticulous, patient deciphering of subtle signals, a quiet act of listening to the universe's most delicate murmurs. This shift, from merely theorizing about other planetary systems to actually detecting them, was akin to moving from drawing maps based on conjecture to actually setting foot on new continents. It fundamentally transformed our understanding of where, or even if, we fit into the grand scheme of things. Imagine, if you will, the collective human consciousness before 1995. Our cosmic home felt relatively contained. The sun, our 8 then 9 planets, and a few rocky outliers. It was a comfortable, if somewhat lonely, cosmic dwelling. The universe beyond was filled with stars. Yes, but those stars were largely seen as solitary beacons, perhaps with fleeting comets or stray asteroids, but not with the intricate gravitational dance of a full-fledged planetary system. The possibility of life beyond Earth, while always a captivating thought, felt much more remote without the confirmed existence of other potential abodes. It was like imagining a bustling metropolis, but only ever seeing a single isolated house. The very fabric of our cosmic imagination was limited by what we could directly perceive or confidently infer. The discovery of that first exoplanet shattered those cozy confines. It was like pulling back a vast, shimmering curtain to reveal a stage far grander and far more populated than we had ever dared to dream. Suddenly, every pinprick of light in the night sky, every distant star, held the tantalizing promise of its own accompanying worlds. The sheer scale of this realization is staggering. Our galaxy alone contains hundreds of billions of stars, and if even a fraction of those stars host planets, then the number of worlds out there is beyond our immediate comprehension. It transforms the universe from a vast, empty expanse dotted with occasional stars into a rich, vibrant tapestry woven with countless celestial bodies, each with its own story, its own potential. This sudden abundance, this revelation of a galaxy teeming with planets, has had a profound impact on our scientific endeavors. It has ignited a furious pace of research, spurred on by the tantalizing question, if there are so many planets, surely some of them must be like our own. Surely some might harbor the conditions necessary for life. This is why, as the text mentions, we are still very much in the early days of this astronomical field. 25 years in cosmic terms is but the blink of an eye. We've only just begun to develop the sophisticated tools and techniques necessary to truly explore this newfound planetary richness. It's like discovering a new continent and having only a small rowboat to begin exploring its coastlines. We have glimpsed the edges of what is possible, and the vast interior remains to be charted. The humble beginnings of this field, rooted in the patient observations of Swiss astronomers, remind us of the power of perseverance and meticulous scientific inquiry. They weren't looking for grand sweeping pronouncements. They were looking for subtle shifts, for tiny clues hidden in the light of distant stars. Their work underscores a fundamental truth of scientific discovery, Often the most profound revelations emerge not from explosive, obvious events, but from the quiet, diligent pursuit of minute details. It's a testament to the fact that sometimes the greatest treasures are found not by shouting, but by listening intently to the softest whispers. The concept that we have confirmed thousands of exoplanets since 1995 itself deserves a moment of quiet contemplation. Each one of those thousands represents not just a data point, but a unique world. A gas giant, swirling in vibrant colors, perhaps with storms larger than our entire Earth. A super-Earth rocky and dense orbiting so close to its star that its surface might be a molten ocean. An ice giant drifting in the frigid outer reaches, shrouded in mysterious clouds. Each discovery adds another brushstroke to the evolving portrait of our galaxy, making it richer, more diverse, and infinitely more fascinating than we ever imagined. This shift in perspective also challenges us to reconsider our place in the universe. If planets are truly ubiquitous, if they are the rule rather than the exception, then the idea of Earth as a uniquely special isolated haven for life begins to soften. It doesn't diminish Earth's beauty or its preciousness, but it broadens our sense of belonging. It suggests that perhaps we are part of a larger, grander cosmic tapestry rather than a solitary thread. This realization, while humbling, is also incredibly liberating. It opens up new avenues of thought and wonder, new questions about the commonality of life, about the potential for other intelligent beings, about the very nature of existence across the vastness. The early days of exoplanet astronomy are also characterized by a spirit of innovation. Because directly observing these faint, distant worlds is so incredibly challenging, scientists have had to invent entirely new ways of seeing. They've had to develop ingenious methods to detect these planets indirectly by observing their subtle effects on their host stars. This creative problem-solving is a hallmark of scientific progress, pushing the boundaries of technology and our understanding of physics. It's like being asked to solve a puzzle with half the pieces missing, and then having to invent entirely new ways to infer the shape and color of those missing parts from the pieces you do have. The growth of this field from one confirmed exoplanet to thousands in just a few decades is a testament to the accelerating pace of scientific discovery. With each new technological leap, with each more sensitive instrument, our cosmic vision expands. What was once purely theoretical becomes observable. What was once unimaginable becomes concrete. This rapid evolution means that the field of exoplanetology is dynamic, constantly surprising us with new types of planets, new orbital configurations, and new insights into planetary formation and evolution. It's an exciting time to be alive to witness these profound shifts in our understanding of the cosmos. And so, as we reflect on these beginnings, on the quiet revolution sparked by that first discovery, we prepare to delve deeper into the specific tools and techniques that allow us to continue this extraordinary exploration. We will soon consider the very first methods used to find these elusive worlds, methods that paved the way for more sophisticated missions like CHOPS. But for now, let this thought gently settle into your mind. The universe is far more populous than we once dared to dream, and every quiet observation, every meticulous measurement, brings us closer to understanding its incredible diversity. The journey of exoplanet discovery is an ongoing story, and we are fortunate enough to be living through one of its most exciting chapters. The stars above are no longer just distant lights. They are signposts to countless other homes, waiting to be characterized, waiting to be understood through the patient, gentle gaze of instruments like CHOPS. As we gently settle into the quiet contemplation of the cosmos, let us now turn our attention to one of the most fundamental challenges in our quest to find other worlds: the veil of brightness. Why is it that even with our most powerful telescopes, simply looking at a distant star known to host planets won't reveal those planets to us? Why is seeing not believing, at least in the traditional sense of direct observation? Imagine gazing at a brilliant lighthouse on a dark, stormy night. Its powerful beam cuts through the gloom dominating everything around it. Now try to imagine a tiny moth fluttering just a few inches from that lighthouse's intensely bright bulb. Even if you knew the moth was there, would you be able to discern its delicate form against the overwhelming glare? This is a tiny terrestrial analogy for the immense challenge faced by astronomers attempting to directly observe exoplanets. The star, our cosmic lighthouse, is so overwhelmingly bright, so intensely luminous, that it utterly hides any small dim planet orbiting nearby. The planet is like that moth lost in the sun's blinding embrace, its very existence swallowed by the overwhelming light of its cosmic parent. This is why when you use a regular telescope to look at stars that are known to have exoplanets orbiting them, you'll only see the intense shine of the star. Its brightness compared to any close orbiting exoplanet is quite simply overwhelming. It's not just a little bit brighter, it's astronomically brighter. We're talking about differences in luminosity that can span billions or even trillions of times. Think of a tiny ember next to a supernova. The contrast is that stark, that absolute. The light from the star simply washes out any faint glimmer that might emanate from or reflect off a nearby planet, making it utterly invisible to our direct gaze. It's like trying to hear a whispered secret in the midst of a thunderous waterfall. The signal is there perhaps, but the noise, the sheer volume of the star's light, is simply too great to discern anything else. Consider our closest stellar neighbor, Alpha Centauri. It's a mere 4 light-years away from us, a cosmic stone's throw in the grand scheme of the galaxy. If we could directly image exoplanets anywhere, you would think it would be there. Yet even around Alpha Centauri, which is relatively bright and close, we cannot directly see exoplanets through a regular telescope. The brilliance of its stars still dominates. This fact alone underscores the immense difficulty of the task. If our closest neighbor remains stubbornly shrouded from direct view by its own light, imagine the challenge of trying to observe exoplanets tens or even hundreds of light-years away. The problem only compounds with distance, as the already faint light from any potential planet diminishes even further across the vast stretches of interstellar space, making the task increasingly arduous, like trying to spot a single grain of sand on a distant beach through a powerful telescope only to find the entire beach is bathed in a blinding spotlight. The concept of a veil of brightness is more than just a scientific term. It's a poetic description of a profound, cosmic truth. The very thing that makes stars the engines of the universe, the majestic sources of light and energy that sustain life and illuminate the cosmic tapestry, is also the very thing that makes their accompanying planets so incredibly elusive. It's a cosmic paradox, an ironic twist of fate. We need the star's light to even know it's there to locate it in the vast darkness, but that same light then becomes an impenetrable barrier, a shimmering wall blocking our view of what orbits so closely around it. It's like trying to discover a secret garden by looking directly into the sun. The sheer, overwhelming brilliance of the sun itself prevents you from seeing the delicate petals and leaves, the hidden pathways, or the quiet beauty that lies within. The garden remains a mystery, not because it isn't there, but because its very existence is overshadowed by the star that nurtures it. This inherent difficulty meant that early astronomers yearning with an almost desperate curiosity to discover worlds beyond our solar system had to think outside the box. They couldn't rely on simply aiming a telescope and expecting to see a tiny dot of light next to a colossal sun, hoping it would miraculously appear. They had to become cosmic detectives, not relying on clear visual evidence, but searching instead for indirect clues, subtle whispers, faint reverberations, rather than direct visual confirmation. It's akin to being in a dark, silent room and knowing someone else is there, not because you can see them, but because you hear a faint rustle of clothes, or feel a slight shift in the air, or detect a subtle change in the room's temperature. These minute changes, though, not directly revealing the source, provide undeniable, compelling evidence of its presence allowing you to infer what is hidden. The overwhelming luminosity of a star isn't just a challenge for our eyes, or even our advanced cameras. It's a fundamental physical barrier, an absolute limit to direct observation in many cases. Imagine sunlight. On Earth, it bathes us in warmth and light, creating the vibrant world we know. Now imagine that sunlight magnified billions of times, concentrated into a single blazing point in the vastness of space. Anything near that point would be utterly dwarfed, not just in its physical size, but more importantly in its emitted or reflected light. A planet, even a massive gas giant, many times the size of Earth, reflects only a tiny, almost infinitesimal fraction of its star's light back towards us. It's like trying to see the faint glow of a firefly's belly on a bright sunny afternoon when the sun is directly overhead. The background light is simply too powerful, too pervasive to allow the delicate luminescence of the firefly to register. The planet becomes a ghost in the cosmic glare, its presence only hinted at by the disturbance it causes, rather than its own fleeting brilliance. This is precisely why the burgeoning field of exoplanetology began with indirect detection methods. It was a profound recognition that if we couldn't conquer the star's blinding light directly, if we couldn't simply outmuscle its brilliance with sheer magnification, then we would have to circumvent it entirely. We couldn't pierce the veil by brute force. We had to find clever indirect ways to peek around its edges to infer what lay hidden behind its brilliant, shimmering folds. This intellectual leap, this pivot from the traditional dream of direct imaging to the ingenious reality of subtle detection, was a pivotal and revolutionary moment in astronomy. It opened up entirely new avenues of research, spurred unprecedented technological development, and forced scientists to think about the universe in fundamentally new ways, leading to the sophisticated instruments and techniques that we employ today. It was a testament to the human capacity for innovation, finding solutions where none seemed to exist. The frustration of this veil of brightness must have been palpable for early astronomers, a constant nagging challenge. For centuries, our telescopes grew larger, their mirrors more perfect, their light-gathering capabilities more immense, capable of seeing further and further into the universe, revealing ever more distant galaxies and nebulas. Yet the closest, most tantalizing prize, planets beyond our own system potentially teeming with life, remained stubbornly, maddeningly out of sight, obscured by the very stars they orbited. It was a constant reminder of the limitations of our direct observational capabilities, a cosmic wall blocking our view of potential siblings in the universe. It forced scientists to get truly creative, to leverage principles of physics that might not seem immediately obvious in the context of seeing a planet, to listen to the silent language of gravity and light distortion. This deep, persistent challenge also highlights the profound, almost overwhelming scale of the universe. When we consider that even planets orbiting stars just a few light years away, practically our next-door neighbors in cosmic terms, are rendered invisible by their host star's light, it emphasizes how truly vast and sparsely populated interstellar space is, and how small and isolated these planetary systems appear from our distant vantage point. It reinforces the notion that even in our closest cosmic neighborhood, the very act of seeing requires immense ingenuity and patience, transforming the pursuit of exoplanets into a quest for the most subtle and delicate cosmic clues. It's like trying to find a single specific drop of water in an entire ocean, not by physically searching for it amidst the waves, but by meticulously analyzing the tiny, almost imperceptible ripples it might create on the surface, or the way it subtly shifts the currents around it. The universe demands a different kind of vision, one that transcends the limitations of our eyes. The fact that we now know of thousands upon thousands of exoplanets, despite this formidable, almost insurmountable obstacle, is a testament to the sheer brilliance, tenacity, and unwavering dedication of generations of astronomers. They did not despair in the face of the overwhelming brightness, did not abandon their quest. Instead, they embraced the challenge, transforming it into an opportunity for innovation, devising clever and often counterintuitive ways to outwit the light itself. They learned to interpret the faintest cosmic whispers, to read the most mind shifts in stellar behavior, transforming what seemed like an impossible task into a thriving dynamic field of discovery that continues to expand our cosmic horizons. This incredible journey from being blinded by the star's radiance to discerning the hidden worlds within its glow is a story of human perseverance, profound scientific insight, and the relentless pursuit of knowledge in the face of seemingly impossible odds. So, as we prepare to explore the ingenious methods that allowed astronomers to overcome this profound challenge, let us hold in our minds the enduring image of that brilliant, overwhelming star, forever concealing its planetary companions within its luminous embrace. It is this fundamental barrier, this veil of brightness, that has spurred some of the most creative and revolutionary approaches in modern astronomy, pushing the boundaries of what we thought was observable. And it is in understanding the depth of this challenge that we can truly appreciate the elegance, the brilliance, and the sheer audacity of the solutions that eventually led us to the discovery of worlds beyond our wildest dreams. The universe doesn't always reveal its secrets easily. Sometimes it requires us to look not at what is most obvious, but at the subtle, indirect clues it leaves behind, like faint footprints in the cosmic dust, or a gentle disturbance in a vast, luminous ocean. This ongoing cosmic hide-and-seek, with the stars playing the role of cosmic guardians of their planetary secrets, defines the very essence of exoplanet hunting. A quest for the unseen, the inferred, the deeply hidden. It's a beautiful, patient dance with the cosmos itself. Having contemplated the overwhelming brilliance that hides distant worlds, let us now gently shift our focus to the ingenious ways astronomers first began to unveil these hidden realms. If the direct view was obscured by the blinding light of the star, how did those persistent cosmic detectives discover the very first exoplanets? The answer lies in a clever indirect method known as the radial velocity method, sometimes also called Doppler spectroscopy. It's like listening for a distant, almost imperceptible hum, rather than trying to see the source directly. Imagine a graceful cosmic dance. You see a large, brilliant dancer, the star, at the center of a vast ballroom. But there's an unseen partner, a much smaller, quieter dancer, the planet, circling around it. Even though you cannot see this smaller partner, its presence still subtly affects the larger one. The star doesn't simply sit perfectly still. It actually performs a tiny rhythmic wobble or gentle sway, pulled ever so slightly by the gravitational tug of its orbiting companion. This delicate, almost imperceptible movement is the key. The star and the planet don't just orbit the star's center. They both orbit around a common center of mass, a kind of gravitational pivot point known as the barycenter. To understand this barycenter, imagine a parent and a child playing on a seesaw. If the parent is much heavier, the pivot point, the barycenter, will be very close to the parent. But both still move around that pivot point. In space, if you have a massive star and a much smaller planet, the barycenter will be very close to the star, perhaps even inside it. However, the star still moves in a tiny elliptical path around this point. If the planet is more massive, or if there are two objects of similar mass like a binary star system, the barycenter might even be a point in empty space between them. One of the most extreme and fascinating examples within our own solar system is the relationship between Pluto and Charon. Instead of Charon orbiting Pluto, they actually orbit a point in space that lies above Pluto's surface. It's a beautifully subtle reminder that gravity's embrace is always mutual, never one-sided. Now, how do we see this tiny stellar wobble from light years away? This is where the magic of Doppler spectroscopy comes in. Think of the sound of a passing ambulance. As it approaches you, its siren sounds higher pitched. The sound waves are compressed or blue shifted. As it moves away, the siren sounds lower pitched. The sound waves are stretched out or red shifted. light behaves in a similar way. If a star is wobbling towards us, its light waves get subtly compressed, shifting slightly towards the bluer end of the spectrum. If it wobbles away from us, its light waves get slightly stretched, shifting towards the redder end. These tiny shifts, almost imperceptible to the untrained eye, can be precisely measured by sensitive instruments, called spectrographs. By carefully analyzing the star's light spectrum over time, astronomers can detect these periodic shifts, the telltale signs of a gravitational dance with an unseen partner. This precise method was how those pioneering Swiss astronomers discovered dimidium, now formally known as 51 Pegasi b. This extraordinary world, a gas giant orbiting a star approximately 50 light-years away in the constellation Pegasus, marked the dawn of exoplanetology. Dimidium is now considered the prototype for what has come to be known as hot Jupiters. Imagine a planet similar in size and composition to our own majestic Jupiter, but instead of orbiting its sun leisurely over many years, it hugs its parent star incredibly tightly. Some of these hot Jupiters have orbital periods of 10 days or less. This means they complete an entire year in less than 2 Earth weeks. Due to their close proximity to their sun, they are, as their name suggests, extremely hot. Their atmospheres, likely superheated and turbulent, a fiery swirling spectacle we can only imagine. The discovery of dimidium, made possible by the LOD spectrograph in France, was nothing short of a scientific marvel. It was the first definitive proof that planets existed beyond our solar system, transforming a theoretical possibility into a tangible reality. This monumental achievement earned the astronomers involved a Nobel Prize, and it was indeed considered a major breakthrough for European astronomy, and truly for all of humanity. It opened a new window onto the universe, changing our cosmic address from a solitary house to one dwelling within a bustling galactic metropolis. The radial velocity method, while groundbreaking, had its limitations. It worked best for hot Jupiters precisely because of their characteristics. Their immense mass created a strong gravitational pull, causing a more pronounced wobble in their parent star that was easier to detect. And their tight orbits meant they completed a wobble cycle very quickly, allowing astronomers to collect multiple data points in a relatively short period, confirming the periodicity of the wobble. Imagine trying to detect the wobble caused by a tiny pebble orbiting a colossal rock. It would be far too small to notice, but a large boulder orbiting a colossal rock that might just cause a noticeable tremor. Hot Jupiters were those cosmic boulders, their massive gravitational footprints leaving clear traces in the stellar light. This method, though indirect, painted a vivid picture of the unseen. It wasn't seeing the planet, but rather observing the star's gravitational dance with the planet. It was like recognizing a hidden instrument in an orchestra by listening to the subtle ways it influenced the melody played by the lead singer. The star's light, meticulously analyzed, became a cosmic seismograph, recording the tremors of distant planetary movements. This was a profound shift in thinking, moving from the desire for direct visual evidence to the acceptance and mastery of inferential observation. It demanded immense patience, precise instrumentation, and a deep understanding of the subtle laws of physics. The radial velocity method's success demonstrated that even when a direct view is impossible, the universe leaves behind clues, subtle hints of its hidden treasures. It teaches us that sometimes the most profound discoveries are made not by gazing directly at what we seek, but by carefully observing its effects on its surroundings. It's a testament to the power of deduction and the elegance of physical laws. The periodic shifts in the star's light, red, then blue-red, then blue again, became the rhythmic heartbeat of a distant unseen world, a silent cosmic drumbeat revealing the presence of a new kind of celestial body. Since that first groundbreaking discovery of dimidium, the radial velocity method, alongside other emerging techniques, has led to a cascade of new exoplanet discoveries. We now understand with increasing certainty that the galaxy is indeed teeming with planets. What was once a philosophical question, a hopeful speculation, is now a scientifically confirmed reality. Every star we look at, or at least a significant fraction of them, might just be the sun to its own family of worlds. This realization has fundamentally reshaped our cosmic imagination, transforming a seemingly vast, empty void into a universe bustling with planetary activity. The journey of exoplanet discovery began with this subtle dance, this hidden wobble. It wasn't about powerful explosions or dramatic visuals, but about precision patience and the ability to interpret the faintest gravitational whispers carried across light years. It set the stage for the next generation of exoplanet hunting, leading to missions like CHOPS, which build upon these foundational insights, taking our ability to characterize these worlds to an even more refined level. The story of Dimidium, the hot Jupiter, and the radial velocity method is a beautiful chapter in humanity's ongoing quest to understand its place in a truly vast and awe-inspiring cosmos. It taught us that even in the face of blinding light, there are always ways to listen to infer and to ultimately uncover the hidden truths of the universe. It's a gentle reminder that the universe reveals its secrets to those who learn to look and listen in new, imaginative ways, pushing the boundaries of what our senses tell us is possible. Having explored the ingenious beginnings of exoplanet discovery through the subtle dance of stellar wobbles, let us now shift our gaze to our quiet, cosmic guide, CHOPS itself. Imagine it, if you will, as a silent sentinel, a tireless observer now gracefully embracing its orbital path high above our planet. It is already performing its crucial work, sending back an astonishing amount of information every single day, more than a gigabyte of data, a steady stream of cosmic whispers reaching us from its perch in the dark. CHOPS doesn't just orbit Earth randomly. It follows a very specific and remarkably clever path, known as a heliosynchronous orbit, situated about 700 kilometers up around Earth. To fully appreciate the elegance of this picture, our Earth slowly spinning bathed in the ever-changing light of the sun. Now imagine CHOPS as a diligent ferry constantly riding along the very edge where day transitions into night, the twilight terminator line. It's always at dawn or dusk from its perspective, perpetually chasing the sun's light around our planet. This unique dawn-dusk polar orbit is a stroke of orbital genius. As CHOPS journeys along this perpetual twilight line, the sun is consistently shining on its back, bathing its solar panels in an unending supply of energy. Think of it as a spacecraft with its own eternal morning, always soaking up the warmth and light it needs to power its delicate instruments. This constant flow of energy means CHOPS doesn't have to worry about running out of power or enduring long periods of darkness where its systems would have to power down. It is always awake, always alert, always ready to receive the faint signals from distant stars. But the brilliance of this orbit extends beyond just power generation. While its back is bathed in sunlight, CHOPS' keen gaze is pointed in the opposite direction, peering deep into space away from our sun. This strategic positioning means its sensitive instruments are perpetually protected from sunlight interference. Imagine trying to observe a faint candle flame across a vast field while a blinding floodlight is shining directly into your eyes. It would be impossible. CHOPS's orbit ensures that its eyes, its highly sensitive photometer and mirror, are always shielded from the overwhelming glare of our own star, allowing it to focus on the truly faint, truly distant objects it is designed to observe. It's like a quiet observer, always standing in the shade, looking out at a brightly lit stage. This tranquil yet purposeful journey through space transforms CHOPS into more than just a piece of hardware. It becomes a living embodiment of quiet diligence. Its heliosynchronous path is a dance of perfect synchronization, a ballet between human design and the immutable laws of celestial mechanics. It's not a frenetic chase, but a measured, steady progress ensuring optimal conditions for its delicate mission day in and day out. Each circuit around Earth is another opportunity, another chance to gather more data, to send more whispers of cosmic truth back to its human creators. The continuous flow of over 1 gigabyte of data every day is like a steady, gentle rain of information. Each drop is meticulously collected, analyzed, and integrated into our ever-growing understanding of the universe. This isn't a burst of overwhelming information, but a consistent, patient accumulation, allowing scientists to build up a rich, detailed picture of the distant exoplanets it observes. Think of it as painting a masterpiece not with a single bold stroke, but with millions of tiny, precise brushstrokes, each adding depth and detail to the canvas. Furthermore, the very solitude of CHOPS's orbital embrace contributes to its effectiveness. High above the Earth's distorting atmosphere, far from the light pollution and the constant hustle of human activity, CHOPS operates in a state of pristine clarity. It's a sanctuary for observation, a quiet chamber where the faint echoes of distant worlds can be heard without distortion or interruption. This quietude is not merely a luxury. It is a fundamental requirement for the kind of precise measurements CHOPS is designed to perform. Every flicker of light, every minute change in a star's brightness carries vital information, and even the slightest terrestrial interference could obscure these crucial signals. The very name, characterizing exoplanet satellite, speaks to its precise purpose. It's not merely finding, it's understanding. And its orbital position is critical to this characterization. By maintaining a stable, predictable, and consistently illuminated environment, CHOPS ensures that the subtle changes it detects are truly astronomical in origin, not artifacts of its own operational environment. This level of environmental control, made possible by its unique orbit, elevates its observations to an unparalleled level of accuracy. Imagine CHOPS as a cosmic librarian, diligently working through vast cosmic archives. Its orbit allows it to remain perpetually focused, its attention undivided by the changing rhythms of day and night that govern our lives on Earth. This sustained observation is vital for its mission, as it allows for long, uninterrupted stares at its target stars. Detecting the minuscule dip in starlight caused by an exoplanet's transit requires continuous monitoring, sometimes for hours or even days. A regular telescope on Earth would be interrupted by sunrise, by clouds, by the very rotation of our planet. CHOPS, however, is free from these terrestrial constraints, a tireless eye that never blinks. This orbital ballet, perpetually chasing the Terminator line, is a beautiful example of how thoughtful engineering can harmonize with the laws of physics to achieve extraordinary scientific goals. It's a quiet testament to the human ingenuity that allows us to extend our senses far beyond our planet's atmosphere, transforming a remote spacecraft into a direct extension of our scientific curiosity. CHOPS, in its perfectly synchronized orbit, becomes a part of the celestial machinery, a small yet powerful cog in humanity's grand quest for cosmic understanding. The data streaming down from CHOPS is not just numbers, it's a language spoken in the subtle variations of starlight, in the rhythmic patterns of brightness and dimness. Each gigabyte represents another chapter in the unfolding story of planetary diversity beyond our solar system. This constant influx of information allows scientists to build up statistical power to detect trends and to confirm even the most fleeting of cosmic events. It's like collecting fragments of a delicate ancient tapestry. The more pieces you gather, the clearer the overall picture becomes, revealing patterns and designs that were previously invisible. And as we consider CHOPS in its orbital embrace, we also acknowledge the immense collaborative effort that brought it to life. The European Space Agency, the Swiss Space Office, and countless engineers, scientists and technicians from various nations have contributed their expertise, their dreams, and their tireless work to make this mission a reality. It is a harmonious symphony of international cooperation, a shared human endeavor to look beyond our familiar skies and understand the wider universe. CHOPS is not just a triumph of technology. It is a triumph of shared human aspiration, a quiet agreement among nations to pool their resources and intellect for the advancement of all. So let the image of CHOPS, this silent, diligent sentinel, gracefully orbiting our Earth on the twilight line, settle softly in your mind. Imagine its solar panels perpetually basking in the sun's embrace, while its sensitive gaze quietly searches the deep, dark expanse of space. It is a beacon of human curiosity, diligently collecting the faint whispers of distant worlds, transforming light into knowledge, and guiding us gently towards a deeper understanding of our place in the cosmic dance. Its journey is a testament to the patient pursuit of truth, a continuous flow of discovery, day after quiet day, night after peaceful night, in its eternal vigil on the edge of Earth's light and shadow. Having quietly observed CHOPS in its perfectly synchronized orbital embrace, let us now gently ponder its most profound ambition, its observation capabilities, and the specific types of celestial bodies it dedicates its tireless gaze toward. Unlike some of its grander, more wide-ranging counterparts like the Kepler telescope, CHOPS' primary goal is not to find new exoplanets. Instead, its mission is one of exquisite precision and deep understanding. It aims to meticulously examine ones we already know about, to determine what they are made of and how they are formed. This subtle shift in focus from discovery to characterization is a profound evolution in our cosmic quest. CHOPS is uniquely equipped to study the smallest exoplanets. We currently understand a fascinating class of worlds known as super-Earths. Imagine a spectrum of planetary sizes. On one end, you have tiny Mercury, barely larger than our moon. On the other, the gas giants like Jupiter, immense spheres of swirling gas and storms. Super-Earths occupy a captivating middle ground. They can be as small as our very own planet, but can also swell to sizes as big as Neptune, which is about 4 times the diameter of Earth. This range makes them particularly intriguing. Are they rocky worlds like ours, perhaps, with a thicker atmosphere? Or are they miniature gas or ice giants, blurring the lines of what we consider a terrestrial planet? CHOPS is designed to help us answer these fundamental questions, to fill in the blanks in our cosmic atlas. The very essence of CHOPS's mission lies in its ability to delve into the intrinsic properties of these distant worlds. It's like having a faint, blurry photograph of a stranger and then being handed a special lens that allows you to discern the texture of their clothing, the color of their eyes, the subtle contours of their face. CHOPS aims to move beyond simply knowing that a planet exists to understanding what that planet is. This pursuit of composition and formation is critical. Are these super-Earths primarily made of rock like Earth and Mars? Do they have substantial metallic cores? Or are they rich in volatile compounds like water ice or methane, perhaps forming vast, deep oceans beneath their surfaces? The answers to these questions are crucial stepping stones in constructing a comprehensive narrative of planet formation across the galaxy. This deep dive into the characterization of exoplanets is truly exciting because it holds the tantalizing potential of discovering potentially habitable worlds. Imagine that for a moment. Not just another rock in space, but a planet that might possess a similar size orbit and composition to our very own home. A place where the conditions might just be right for liquid water to exist on its surface, where the temperatures are neither too scorching nor too freezing, where the atmosphere could potentially support the delicate chemistry of life. CHOPS is specifically engineered to look for these subtle signs, these cosmic fingerprints that whisper of habitability. Think of it not as a frantic search for alien life itself, but as a meticulous survey of potential cradles for life. If we can understand the building blocks of these planets, their internal structure, and the gases swirling in their atmospheres, we move closer to identifying those rare precious gems in the cosmic expanse that might truly be siblings to our Earth. This is the quiet hope that hums at the heart of the CHOPS mission, the possibility that among the thousands of dots of light we now know are planets, some might truly be our cosmic kin, sharing the right conditions that harbored life here on our blue marble. The significance of this mission cannot be overstated. It represents a paradigm shift from broad surveys to targeted investigations. It's akin to an explorer, after discovering a vast new continent, deciding to focus on meticulously mapping specific regions, analyzing the soil, identifying the flora and fauna, and assessing the potential for life within those particular valleys and mountains. CHOPS is performing that detailed critical analysis for the most promising exoplanets we've found so far. It's a testament to the fact that discovery is often just the beginning of a much deeper, more intricate scientific journey. The data CHOPS collects on composition is paramount. For instance, if a super-Earth is found to be far less dense than a purely rocky world of its size should be, it could indicate a substantial amount of water or other volatile compounds in its makeup, perhaps suggesting an ocean world with a deep global ocean beneath a thick atmosphere. Conversely, a very dense super-Earth might suggest a higher metal content or a very compact rocky interior, hinting at a different formation history. Each piece of information adds another detail to the cosmic puzzle. Moreover, understanding how these planets are formed provides crucial insights into the broader processes of planetary evolution throughout the galaxy. Do planets primarily form in the same way? Or are there diverse pathways to planetary creation? Do super-Earths form in situ in the very orbits where we find them? Or do they migrate inwards from colder, more distant regions of their stellar systems? The answers to these questions help refine our models of planet formation, allowing us to better predict where and what kinds of planets we might find in the future, and how common worlds like our own might truly be. The quiet pursuit of these fundamental questions is what makes CHOPS so compelling. It's not about sensational headlines, but about the slow, steady accumulation of knowledge that builds a truly profound understanding. It is about patiently gathering evidence, analyzing it rigorously, and then carefully piecing together the story of these distant worlds, one data point at a time. This methodical approach is the bedrock of true scientific progress, allowing us to move from speculation to robust evidence-based conclusions. Imagine the subtle differences that CHOPS is designed to detect. A slightly different radius, a minute variation in the planet's atmospheric signature, a tiny difference in its orbital inclination. Each of these details, seemingly small in isolation, contributes to a holistic picture of the exoplanet. It's like studying an ancient artifact. You don't just admire its beauty, you meticulously analyze its material, its craftsmanship, its wear and tear to understand its history, its purpose, and its cultural significance. CHOPS is performing a similar archaeoastronomical analysis on worlds light years away. The ultimate vision for CHOPS is to inform future missions. The more we understand about the variety of super-Earths and their potential for habitability, the better equipped we will be to design the next generation of telescopes, even larger, more powerful instruments that might one day be capable of directly imaging these worlds or even analyzing their atmospheres for definitive biosignatures, the chemical imprints of life itself. CHOPS is laying the groundwork, building the foundational knowledge that will guide humanity's search for life beyond Earth for decades to come. This mission embodies a deep sense of cosmic responsibility. We are not just exploring for exploration's sake. We are trying to answer one of humanity's most enduring questions. Are we alone? And if not, where are our cosmic neighbors and what are they like? CHOPS provides a tangible scientific pathway towards addressing these profound queries, not with fleeting hopes, but with concrete data and rigorous analysis. It is a testament to the meticulous, patient, and often quiet work that underpins humanity's grandest scientific endeavors. So as we consider CHOPS's specific quest to characterize super-Earths and search for potentially habitable worlds, let a sense of quiet wonder fill your mind. Imagine those distant planets, perhaps with continents, oceans, and atmospheres waiting to reveal their secrets through the careful measurements of our orbiting eye. CHOPS is not just looking for planets, it is looking for possibilities for the potential echoes of life, for worlds that might in their own unique way remind us of home. And in that gentle pursuit, it brings us closer to understanding the true richness and diversity of the cosmos. One characterized exoplanet at a time, whispering its secrets across the vast starlit expanse. Now let us delve into the truly counterintuitive heart of CHOPS's ingenious design, the very paradox we introduced at the beginning of our journey, the art of the blurry. Why would a space telescope built with such precision and sent to such a distant vantage point be designed to capture images where all the stars are indistinct, seemingly out of focus with no exoplanets visibly distinct? This isn't a design flaw, a gentle whisper of imperfection. Rather, it is CHOPS working exactly as intended, embodying a revolutionary way of seeing more by seeing less. Imagine for a moment a master artist, not painting with sharp, precise lines, but with a deliberate soft focus blurring the edges to capture the essence of light itself. CHOPS is much smaller than the grand, iconic Hubble Space Telescope. It's only 1.5 meters across and uses a modest 32-centimeter mirror. Yet it can see exactly what its brilliant designers had hoped for. If you were to see those first images from CHOPS, you might indeed notice something peculiar. All the stars captured in them are a soft, diffuse blur with no exoplanets directly visible within that haze. This seems perplexing, doesn't it? Like buying a high-resolution camera only to intentionally set it to a blurry mode. The reason for these exquisitely blurred images has everything to do with the second and arguably most productive method of exoplanet discovery and characterization: transit photometry. Think of it as a tiny cosmic eclipse if an exoplanet's orbit is perfectly aligned with our line of sight. From Earth, it will occasionally pass directly in front of its parent star. From our perspective, the planet will cover a tiny fraction of the star's disk, causing a minuscule temporary dip in the amount of light we receive from that star. It's a delicate cosmic wink, a brief shadow cast across a distant sun. One of CHOPS's key instruments is a very advanced photometer, a light measuring device so sensitive it can detect the tiniest amount of light variations on distant stars. This photometer is the very heart of its blurry vision strategy. CHOPS constantly monitors the amount of light it receives from a specific target star. When a planet crosses in front of its disk, CHOPS meticulously records how much dimmer the star gets. The degree of dimming and the duration of the dimming event can tell us a surprising amount about the planet's size and orbital period. Relative to its star, a larger planet will obscure more light, causing a deeper, more noticeable dip, while a smaller planet will cause only a very shallow, fleeting dip, barely a ripple on the surface of the star's light. Now for the crucial part. The reason the CHOPS image is blurry is so that light from the star hits more of the camera sensor, increasing the number of pixels that get hit by the star's light. Instead of trying to focus the star's light onto a single sharp point, a single pixel, CHOPS deliberately spreads that light out over a small diffuse area. Imagine trying to collect raindrops in a tiny thimble versus a wide, shallow pan. The thimble might give you a sharp, concentrated drop, but the pan collects far more water overall, even if it spreads it out. Through this deliberate blur, astronomers don't actually need to see the exoplanet itself as a distinct object. In fact, trying to image such tiny, faint objects next to blinding stars is generally impossible with current technology, as we discussed in our previous chapter on the veil of brightness. Instead, this increased resolution, paradoxically achieved through blurring, allows astronomers to accurately record and study the star's light spectrum itself, as well as any minuscule changes that take place from the exoplanet's transit. Let's explore this fascinating concept of blur in more detail. When light from a distant star enters CHOPS, it's not focused into a pinpoint. Instead, it's deliberately defocused, just enough so that the light from the star spreads out, creating a small soft circle of light on the detector. Why is this so powerful? Because a single pixel on a detector can become saturated, overwhelmed by too much light, leading to inaccurate readings. But by spreading the light across multiple pixels, CHOPS can measure the total amount of light with far greater precision and accuracy. Each pixel contributes its small portion of the total light, and by summing these contributions, scientists can build an exquisitely precise measurement of the star's overall brightness. This technique is especially vital for detecting and characterizing small planets, those tiny elusive worlds that might truly be more Earth-like. As you can guess, the bigger the planet, the more light it will obscure, and the easier it will be to notice a dip in light intensity. For small planets, however, this process is much more difficult to measure. The dip in brightness might be only 1 part in 10,000 or even 1 part in 100,000. It's like trying to detect a single grain of sugar dropped into a vast swimming pool. CHOPS's advanced instruments and its unique blurry image approach allow astronomers to better define the transits of those smaller, more Earth-like planets, extracting every last whisper of information from their fleeting shadows. It allows for a much higher signal-to-noise ratio for these tiny dips, effectively reducing the noise from the star itself. By distributing its light more evenly, think of it this way. If you try to put all the light onto one pixel, that pixel quickly gets overwhelmed, and any subtle change in light might be lost in the saturation. But by spreading the light, you effectively create many mini-pixels, each receiving a small manageable amount of light. When the planet transits, all these pixels will show a tiny collective dip in brightness, and by adding up those tiny dips across the blurred image, the overall change in the star's light becomes much clearer and more measurable. This is why CHOPS is so important. Its innovative design allows for the unparalleled photometric precision needed to discern the subtle signatures of truly small exoplanets. Furthermore, this blurring technique helps to mitigate the effects of minor cosmic phenomena that could otherwise introduce noise into the data. For instance, tiny imperfections in the telescope's optics or slight movements of the spacecraft could cause the star's image to shift slightly on the detector. If the image were perfectly sharp, this slight shift could move the star's light off a single pixel and onto another, creating a false signal that looks like a change in brightness. But with a blurred image, the star's light is already spread out, so a minor shift doesn't significantly change the total amount of light hitting the detector. It's like pouring water into a wide bowl. A little tilt won't spill much, but with a narrow, tall glass, a slight tilt can cause a lot of spillage. This robustness makes CHOPS's measurements incredibly reliable. The success of the transit photometry method enabled by designs like CHOPS's blur also underscores a profound philosophical point. Sometimes to understand something truly deeply, we must look at it not directly, but through its interactions, its effects on its surroundings. We don't see the planet, but we see the story it writes in the light of its star. It's a testament to the fact that the universe often communicates in subtle whispers rather than bold statements, and our task as cosmic listeners is to tune our instruments to hear those whispers. The beauty of this method lies in its elegant simplicity and its profound implications. By precisely measuring the timing and depth of these stellar winks, astronomers can not only determine the planet's size relative to its star, but also its orbital period. Knowing the orbital period, coupled with measurements of the star's mass, allows scientists to infer the planet's orbital distance from its star. And with that, they can estimate the planet's approximate temperature, a crucial factor in assessing its potential for habitability. It's a cascade of information, each piece unlocking the next, all from a tiny dip in a distant star's light. So the next time you hear about a blurry image from CHOPS, remember that it's not a flaw, but a feature. It's not a sign of imperfection, but a testament to human ingenuity in overcoming the profound challenges of seeing across vast cosmic distances. It is the art of the blurry revealing the subtle beauty and profound truths of distant worlds, allowing us to read the quiet story written by a planet as it passes through the light of its sun. This unique design allows CHOPS to fulfill its critical mission of characterizing the most promising exoplanets, moving us ever closer to understanding the true diversity of worlds in our galaxy, and perhaps even finding another home among the stars. It is a quiet revolution in perception, turning what was once a hindrance into a powerful tool for discovery. Having understood the elegant paradox of Chops's blurry images and its mastery of transit photometry, let us now gently turn our attention to an even more subtle and profound capability of this remarkable satellite: its ability to decode the atmosphere of distant worlds by measuring their phase curve. This is where the light we receive begins to speak a richer language, whispering not just about a planet's size, but about its very essence, the gases that swirl in its sky, the elements that make up its being. Imagine a distant planet caught in the intricate dance of its orbit around its star. When this planet is directly in front of its star during a transit, it blocks a tiny amount of the star's light, creating that momentary dimming we've discussed. But the story of light doesn't end there. As the planet continues its journey around the star, moving from being directly in front to orbiting around its sides, something else subtly begins to happen. It starts to reflect light back to us from its sunlit side. Just like our moon goes through phases, from new moon when its sunlit side faces away from us, to full moon when its sunlit side faces us, an exoplanet also has phases. When the planet is at its full phase, meaning its fully illuminated side is facing both its star and us, it will reflect the maximum amount of light back towards our telescopes. This reflected light, incredibly faint as it is, will actually make the star appear a little bit brighter from our perspective than it would if the planet wasn't there reflecting light. It's a minuscule, almost imperceptible increment in the star's overall brightness, a whisper added to a roaring symphony. This is precisely where Chops's incredibly sensitive photometer comes in handy again. This time, it's not looking for a dip in light, but rather measuring this tiny, delicate increment in light variation. To understand the profound importance of this, think of it as a cosmic scale. When the planet is behind the star, its reflected light is completely blocked from our view. At this point, we are receiving only the pure, unadulterated light from the star itself. This serves as our baseline, our control measurement. Then, as the planet emerges from behind the star and begins its orbit, its reflected light gradually adds to the total light we receive, reaching a peak when the planet is at its fullest phase from our perspective. By meticulously comparing the total light we receive when the planet is in front of the star blocking light, to the light we receive when the planet is behind the star when it's not interfering with the star's brightness, scientists are able to isolate the spectrum of the light reflected by the planet itself. This is an astonishing feat, akin to listening to a grand orchestra and trying to isolate the sound of a single tiny flute, not by directly hearing it, but by comparing the full orchestral sound to when that flute is momentarily silent. With the isolated spectrum of the light reflected by the planet, scientists can then begin to know the composition of the planet's atmosphere. Different gases and molecules absorb and reflect light at specific wavelengths, leaving unique fingerprints in the light spectrum. For example, the presence of certain absorption lines could indicate water vapor, carbon dioxide, methane, or even tantalizingly, oxygen. And since CHOPS is not on a broad discovery mission, but rather is investigating only the most promising planets, it can dedicate significant sustained observation time to these targets. This means it can take multiple readings of the phase curve over many orbital cycles, allowing for a more defined measurement. This repeated observation reduces noise averages out any random fluctuations and strengthens the signal of the incredibly faint reflected light. It's like taking many blurry photographs of the same scene and then painstakingly layering them together to reveal a hidden pattern, a secret code written in light. The ability to determine atmospheric composition is a monumental step in the search for life beyond Earth. While detecting water vapor or carbon dioxide doesn't automatically mean life exists, it tells us if the fundamental ingredients for life as we know it are present. The ultimate prize would be the detection of biosignatures, combinations of gases like oxygen and methane that, when found together in significant quantities and out of chemical equilibrium, strongly suggest the presence of biological processes. CHOPS is meticulously collecting the data that could in time help us identify these potential markers. The phase curve also provides other valuable information. The way the light varies as the planet orbits can reveal details about the planet's albedo, how reflective it is, its cloud patterns, and even its surface features if it's a rocky planet. A planet with extensive cloud cover, for instance, might have a higher albedo and a different phase curve shape than a cloudless rocky world. It's like watching a distant, shimmering marble slowly turn, and by noting how the reflections shift, you can infer the textures and contours of its surface. This meticulous analysis of light, stretched and squeezed, absorbed and reflected, speaks to the immense precision required for modern exoplanetology. We are no longer just counting dots in the sky. We are reading the subtle stories encoded within those dots of light, deciphering the very chemical makeup of worlds billions of miles away. It's a truly profound act of cosmic listening, using the universal language of light to understand the silent, unseen worlds that share our galaxy. The dedication to taking multiple readings, focusing on the most promising planets, speaks volumes about the strategic importance of CHOPS. It's not a broad sweep net. It's a highly specialized probe designed for in-depth analysis. This focus allows for an unparalleled level of data quality, pushing the boundaries of what's possible in atmospheric characterization. Imagine a detective focusing all their resources on a few key clues, meticulously analyzing every detail, rather than spreading themselves thin across countless leads. This targeted approach significantly increases the chances of a breakthrough. The information derived from phase curve measurements will feed directly into our understanding of planetary habitability. If we can confirm the presence of certain molecules in an exoplanet's atmosphere, it paints a more complete picture of its environment. Does it have a thick, suffocating atmosphere or a thin, tenuous one? Is it rich in water or bone dry? These are the questions that move us beyond mere speculation and into the realm of empirical knowledge, inching us closer to identifying a truly Earth-like twin in the cosmos. Moreover, the successful measurement of phase curves by CHOPS validates the complex theoretical models that predict how light should behave when interacting with a planet's atmosphere. Every confirmed measurement strengthens our understanding of the physics involved, allowing scientists to refine their models and make even more accurate predictions for future observations. It's a continuous loop of theory and observation, each informing and elevating the other. This detailed atmospheric analysis is also crucial for understanding planetary evolution. How do atmospheres form and evolve on different types of planets? What causes some planets to lose their atmospheres while others retain thick envelopes of gas? By studying the atmospheric composition of a diverse range of exoplanets, CHOPS contributes to a broader understanding of how planets, including our own, come to be and change over cosmic timescales. It's a window into the dynamic history of worlds, revealing their past and hinting at their future. So as CHOPS meticulously tracks these distant worlds, measuring every nuanced flicker and surge of reflected light, it embarks on a quiet quest to reveal their innermost secrets. It is listening for the subtle chemical signature, the unique atmospheric fingerprint that might speak of oceans of weather and perhaps of life. This ability to decode the atmosphere piece by careful piece brings us incredibly close to answering one of humanity's most enduring questions, transforming faint light into profound knowledge. It's a beautiful symphony of science and patience, playing out across the vast stages of interstellar space, patiently waiting for the universe to reveal another one of its breathtaking wonders. As we contemplate the remarkable capabilities of CHOPS from its blurry vision, revealing transits to its delicate decoding of reflected light. For atmospheric clues, a fundamental question gently arises. Why does CHOPS have to be in space? Could we not accomplish all these exquisite readings from our own beautiful, familiar Earth? The answer, while seemingly simple, carries profound implications about the very nature of observation and the persistent challenges our home planet presents to our cosmic gaze. Just like the Grand James Webb Space Telescope, or even the venerable Hubble before it telescopes here on Earth, face two primary unyielding hurdles that severely limit their ability to perform the kind of precise, continuous observations that CHOPS excels at. These hurdles are woven into the very fabric of our terrestrial existence, constant companions that remind us of our grounded reality. The first hurdle is perhaps the most obvious yet often underestimated in its impact: the relentless cycle of night and day. We live on a spinning globe bathed in the warmth and light of our sun for roughly half of any 24-hour period. This means that for a large section of every single day, no astronomical observations of faint distant objects can take place from any given terrestrial observatory. Imagine trying to read a very faint detailed map under the blazing midday sun. It simply wouldn't work. The sky, our canvas for cosmic observation, becomes a blinding, featureless expanse during the day. This means that a telescope on Earth, no matter how powerful, is inherently limited in its observing time. A crucial exoplanet transit, a tiny dip in stellar brightness that might only last for a few hours, could easily be missed if it happens to occur during the local daytime. It's like trying to catch a fleeting glimpse of a rare bird that only appears at very specific, unpredictable moments. If you're asleep or otherwise occupied during those crucial seconds, you miss it entirely. The rhythm of Earth's rotation, while vital for life, imposes a frustrating discontinuity on our astronomical observations, a broken line in the continuous stream of cosmic data. But even when the sun dips below the horizon and night unfurls its star-strewn canopy, another formidable obstacle remains Earth's atmosphere. This protective blanket of gases so essential for our survival becomes a shimmering turbulent veil for light traveling from distant stars. As starlight journeys through the various layers of our atmosphere, it encounters countless particles, molecules of air dust water vapor. Each encounter causes the photons of light to scatter, to bend, to refract in unpredictable ways. This constant disturbance makes the light flicker and wobble as it reaches our telescopes, like trying to see a perfectly still object through agitated water. Think of it as looking at the bottom of a swimming pool on a hot day. The light rays shimmer and distort, making the tiles on the bottom appear to dance and blur. This atmospheric distortion, known as seeing in astronomical terms, is the reason stars twinkle in our night sky. While beautiful to the naked eye, this twinkling is a bane for astronomers. It blurs images, spreads out the light, and makes it incredibly difficult to obtain the sharp, precise, and stable measurements required for delicate tasks like transit photometry or phase curve analysis. Every single photon of light, after traveling billions of miles through the pristine vacuum of space, faces this final turbulent gauntlet in its last few miles, just before reaching our detectors. While there are several clever methods to counter some of these atmospheric distortions from Earth, techniques like adaptive optics, which use deformable mirrors to compensate for atmospheric blurring, these readings would never be as accurate, as pristine, or as continuous as they would be in the tranquil vacuum of space. Adaptive optics can sharpen images, but they cannot eliminate all distortions, nor can they magically extend observation time through the day. They are powerful tools, but they work within the fundamental limitations of being Earth-bound. This is precisely why CHOPS was launched into a sun-synchronous orbit, as we explored in an earlier chapter. This isn't just a convenient orbital path. It's a strategically chosen cosmic perch designed to completely circumvent the two primary terrestrial hurdles. As I mentioned before, it will perpetually ride the terminator line of Earth, that thin, ever-moving boundary between light and shadow. This unique orbit serves a dual purpose, each vital to CHOPS's success. Firstly, it allows the satellite to receive constant light on its back for the solar panels to generate power. This provides an uninterrupted energy supply, eliminating the need for bulky batteries that would add weight and complexity, and ensuring that CHOPS's delicate instruments are always fully powered and ready for observation. It's like having an infinite power cord stretching directly to the sun, ensuring continuous operation. Secondly, and equally importantly, for its scientific mission. This sun-synchronous orbit means CHOPS can take a look at stars 24/7 without sunlight interfering with its readings. Because its instruments are always pointed away from the sun into the deep dark expanse of space, they are never blinded by the overwhelming glare of our own star. This allows for uninterrupted continuous monitoring of target stars, which is absolutely critical for catching the brief, subtle transit events and for building up enough data over many orbital cycles to precisely measure a phase curve. Imagine trying to collect tiny, almost invisible dust particles from the air. You need a perfectly still, perfectly clean environment to do so effectively. Space provides that environment. Consider the immense advantage of this continuous observation. A transit event might only last for a few hours. If your telescope on Earth can only observe at night, and that transit occurs during the day, you've missed it. If clouds roll in, or if the moon is too bright, or if other atmospheric conditions are unfavorable, the observation window closes. CHOPS, however, is impervious to these terrestrial whims. It operates above the clouds, above the distorting atmosphere, and in a constant state of cosmic night from its observational vantage point. It is the ultimate patient observer capable of staring at a single star for days or weeks on end, waiting for that subtle wink, that fleeting shadow that tells the story of an orbiting world. This stability and consistency are not mere conveniences. They are fundamental requirements for the kind of high-precision photometry CHOPS performs. To detect light changes as small as 1 part in 10,000, every source of noise must be meticulously eliminated or controlled. The Earth's atmosphere is a chaotic, unpredictable source of noise. By elevating CHOPS above it, we remove the primary source of signal distortion, allowing the telescope to detect the true pristine variations in starlight untainted by our planet's turbulent breath. The decision to launch CHOPS into space therefore represents a profound commitment to accuracy and efficiency. It acknowledges that while Earth-based astronomy has its place and its unique advantages, certain types of observations simply demand the clear, uninterrupted view that only space can provide. It's a strategic investment in achieving unparalleled precision, pushing the boundaries of what we can discern from the faint signals that traverse the cosmos. Moreover, the absence of atmospheric distortion means that CHOPS's observations are inherently more reliable. There's less need for complex algorithms to undo the effects of the atmosphere, meaning the raw data itself is closer to the true cosmic signal. This simplifies data analysis and increases confidence in the results, allowing scientists to draw more robust conclusions about the exoplanets they are studying. It's like listening to a piece of music through crystal-clear headphones rather than through a muffled, static-filled speaker. Every note, every nuance becomes distinct. In essence, placing CHOPS in space transforms it from a terrestrial observer into a true cosmic resident, unburdened by the diurnal rhythms and atmospheric turbulences of its home world. It is a tireless eye perpetually open, continuously gathering the precious photons that hold the secrets of distant exoplanets. This orbital sanctuary is not just a location. It is an optimized laboratory, providing the perfect conditions for the delicate art of characterizing worlds light years away. So, as we imagine CHOPS silently gliding along Earth's twilight edge, collecting its constant stream of data, let us appreciate the profound wisdom in its orbital design. It is a testament to humanity's determination to overcome challenges, to push beyond limitations, and to create the purest possible window into the vast, mysterious universe. It is a promise that even when our own world tries to obscure our cosmic vision, our ingenuity will find a way to pierce through, to see more clearly, and to listen more intently to the ancient silent whispers of the stars. The sky above is not just a ceiling, it is a portal, and CHOPS is our quiet, steady hand, holding it open, allowing the light of distant worlds to pour in undisturbed and true. And so we arrive at the final gentle chapter of our cosmic contemplation, guided by the silent, diligent work of CHOPS. As we have seen this remarkable satellite, with its counterintuitive blurry vision and its unwavering gaze from orbit, is meticulously gathering the most precious of cosmic data. With all the information CHOPS will hopefully collect, we stand at a precipice of profound discovery. It may just be a matter of time until we can confirm the existence of another planet like Earth. Imagine that possibility for a moment. A world, not just a distant speck of light, but a planet with similar mass and temperature to our own. A world where the delicate balance of distance from its sun, coupled with its size, allows for conditions that mirror our familiar home. A place where the temperatures are neither too scorching to boil away all liquid, nor too frigid to freeze it solid. This Goldilocks zone, where conditions are just right, is the first crucial ingredient in the recipe for habitability. CHOPS, by refining our understanding of exoplanet sizes and orbital characteristics, brings us ever closer to identifying these prime candidates. But the true prize, the tantalizing whisper that CHOPS is designed to listen for, is the presence of water and oxygen in its atmosphere. Water, the very elixir of life as we know it, is paramount. If CHOPS can detect the telltale spectral fingerprints of water vapor in a distant atmosphere, it would be a monumental step. It would suggest the potential for liquid water on the surface, or at least within the planet's interior, providing the universal solvent that life requires. Oxygen, specifically free oxygen, is another powerful indicator. On Earth, the vast majority of free oxygen in our atmosphere is produced by living organisms through photosynthesis. Its presence in a distant exoplanet's atmosphere, especially in combination with other gases that would otherwise react with it, could be a compelling biosignature, a cosmic exhale from alien life itself. These are all the right conditions that harbored life here on our blue and green oasis. The intricate dance of liquid water, a stable temperature range, and a breathable atmosphere teeming with life-sustaining gases. These are the foundational elements that allowed complex life to flourish on Earth. CHOPS, with its exquisite precision in analyzing transits and decoding phase curves, is methodically searching for these very conditions, systematically narrowing down the vast cosmic haystack to find those rare precious needles that might truly be cosmic twins to our home. The implications of such a confirmation are almost too vast to fully comprehend. For millennia, humanity has gazed at the stars and pondered our uniqueness. Are we alone in this boundless universe? Is Earth a singular miracle, a fluke of cosmic chance, or is life in its myriad forms a common thread woven throughout the cosmos? CHOPS may not provide a definitive answer to the existence of alien life, but it could provide the strongest evidence yet that the potential for life is not unique to Earth. It could show us that the universe is not just vast and silent, but vast and potentially teeming with habitable real estate awaiting the blossoming of its own unique ecosystems. Imagine the ripple effects of such a discovery. It would fundamentally alter our philosophical outlook, our sense of place in the universe. It might inspire new generations to look up with even greater awe, to dream of interplanetary travel, to ponder the shared journey of life across the cosmos. It would be a testament to humanity's enduring curiosity, a vindication of the immense effort and ingenuity invested in missions like CHOPS. This is not a search for little green men or for immediate contact with advanced civilizations. This is a scientific, methodical search for the conditions that could lead to life, a profound endeavor to understand the commonality of planetary systems and the distribution of life-favorable environments. It is a slow, patient, unveiling a meticulous analysis of light that may one day reveal the ultimate secret that the universe is perhaps far more alive than we ever dared to dream. The continuous flow of data from CHOPS is like a steady, gentle rain slowly filling the reservoir of our knowledge. Each gigabyte, each transit observed, each phase, curve measured, contributes to a grand mosaic, and as this mosaic takes shape, we gain a clearer, more nuanced picture of the true diversity of exoplanets. We learn about rocky worlds, gas giants, ice planets, and crucially those super-Earths that might bridge the gap between our understanding of our own solar system and the grander, more varied planetary architectures of the galaxy. The journey of CHOPS is a testament to the power of international collaboration and a shared human vision. Scientists and engineers from different nations speaking different languages have come together with a common purpose to push the boundaries of human knowledge and to answer some of the most profound questions of our existence. This spirit of cooperation, mirroring the interconnectedness of the cosmos itself, is a beautiful aspect of modern astronomy. As we conclude our time together, let the image of CHOPS, our quiet, tireless sentinel, linger softly in your mind. It is a symbol of our collective yearning to understand, to connect, and perhaps to find a reflection of ourselves among the distant stars. Its mission, built on ingenuity and patience, reminds us that the greatest discoveries are often made not with a sudden flash of insight, but with persistent, meticulous work, one gentle observation at a time. So as you drift into dreams, carry with you the thought of those distant worlds, perhaps waiting to reveal their secrets through the careful measurements of CHOPS. The universe is full of wonders, both seen and unseen, and our understanding of it is an ever-unfolding story. The search for another Earth with water and oxygen in its atmosphere, with all the right conditions that harbored life here, is not just a scientific quest. It is a profound journey of self-discovery, reminding us of the preciousness of our own home and the boundless possibilities that lie beyond. Thank you for listening to this podcast on the Characterizing Exoplanet Satellite. If you enjoyed what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McCohen, and this has been Astrom. All the best, and may your dreams be filled with starlight and the quiet promise of new worlds.